Hello, everyone. Welcome to another session of the AFMS seminar. It's my great pleasure to introduce today's speaker, Professor Josué Sznitman from Technion. Professor Josué completed his education from MIT and ETH Zurich and has worked at University of Pennsylvania and Princeton University before joining Technion. His research is on respiratory transport phenomena and pulmonary physiology, with a focus on preclinical models and drug delivery to the lungs, including inhalation therapy. Most notable amongst his many accolades is the Young Investigator Award by the International Society of Aerosols in Medicine 2015, and the Emerging Scientist Award in Drug Delivery to the Lungs by the Aerosol Society of UK in 2018. And today he will talk on revisiting airflow and aerosol transport phenomena in the deep lungs. So over to you, Josué.
Thank you, Vishal, for the kind introduction. It's a pleasure to be here. I know we had scheduled several months ago this talk, and as you know, when everybody logs in from different places in the world, it's kind of hard to pinpoint a time, but we've made it. So a couple of anecdotal things. I had the opportunity to go twice to Australia. Once, my very first time was in 2008 in Adelaide. I don't know if those of you might remember. There was one of the big ICTAM Congress, I think that's what it's called, the kind of mechanics societies was having their international Congress there. And then I came again in late 2016. A good friend of mine and also a quite well-known fluid dynamicist, Leslie Yao from RMIT, who I've known for many, many years, hosted me, and he's currently in Cambridge. And the last link for me is my former postdoc advisor, Alexander Smits, who I guess some of you might know, who's, well, originally from the Netherlands, but is an Australian with whom I just chatted actually a day ago, is from Melbourne. So anyways, what am I going to tell you today? I'm going to tell you things that I understand, things that I don't understand, but mostly I want to give you some insight on what I've learned for 15 years or so, 15 odd years since I've invested basically the bulk of my career in the world of respiratory phenomena. Just a short word, I'm actually just wrapping up now my sabbatical. So for those of you who don't know, I carry a few passports in my hand, but I'm Swiss, and I took the opportunity after COVID to do my sabbatical at home. And I was hosted at a biomechanics lab at the EPFL, where I was a visiting professor. And now it's time to get back to business. So we're starting our semester here. And some of the sources over the years that have funded the research that has helped us push through. Okay, so I'm, in some sense, I enjoy doing scientific storytelling and building up a little bit a kind of the stakes. So the first thing I think is important in understanding what's about to come is setting the stage. And I'm not going to talk about everything to do with the lungs first because we don't have time, but that's an easy excuse. It's because I probably don't understand it. So what I'm going to focus on, and it's historically where I started my career, it's the notion of the deep lungs. All right. So in this Crash Course 101, the things since I'm addressing mostly fluid mechanics and mechanics audience, is one of the emanating pieces that have really pushed and kind of motivated my career is why on earth did I feel so passionate about the lungs? It could have been any other organ, you could say. But as an engineer, and it biases for good and bad my viewpoint, what's fascinating in this organ is the concept of the length scales. And of course, this is a terminology and a jargon that we use all the time in fluid mechanics. Well, it really holds true here because this organ spans from the mouth down to the deep alveolated airways, or the acinus. We'll be using interchangeably those words. Basically up to, depends how you count, 3 to 4 orders of magnitude. So the trachea, the typical length scale of the diameter of your trachea is on the centimeter scale. As you go through the main bronchi to the smaller bronchi, bronchioles, terminal bronchioles, acinar space, I've tried to show you that in this landscape, you cross through about down to something like an alveolar sac. The alveolar lens case, this diameter, you know, it's certainly nothing like what's illustrated here in terms of the morphology and the anatomical construct, and I'll get to that, but just to show you, we're talking about 100 microns. Just as a side note, for those of you interested in everything to do with perfusion, cardiovascular system, and in particular capillary flows, well, don't forget that the fine mesh that lined each alveolar wall is on the order of 5 microns, which is the size of a red blood cell. So in that sense, you probably span up to, say, 5 orders of magnitude. Okay. So typically, if you take something like an annual review of fluid mechanics, you'll see this kind of breakdown. And I'm only using here for you to kind of situate yourself, okay? So the idea is basically you can think of the lungs as a 2-part system. One is what we call the conductive airways. Vishal, can you tell me if you guys see my mouse? Or maybe I should use the pointer option.
Okay, I can see your mouse.
Lovely.
Yeah, I can see the pointer as well now. Yeah.
Perfect. So what I think our eyes and what we're accustomed to is that we think of the lungs as the conducting airways. We think of the larger airways, which are what I would say in simplified term, it's basically the highway, right? This is a transport network. At the end of the day, it needs to bring oxygen to the deep space where it's going to be subject to gas exchange across the alveolar wall into the capillary bloodstream. And then the respiratory zone, which is basically everything that encompasses the presence of an alveolus, from the terminal bronchi, what we call here exactly the cutoff point, the respiratory bronchi. So respiratory here entails that there are already alveoli. Now, what is less kind of intuitive is that actually 90% of all the lung volume is captured in something on the order of 500 million alveoli. But at the large scales of our eyes, what we only see is, of course, the what we call the main and upper airway tract. Okay, so a little bit of, there's not going to be so many equations, but again, my business here is to first situate the audience. And historically, I'd say that the first kind of landmark review, to the best of my knowledge, is in the work of our dear Tim Pedley, who was very active in the field. And you can pick up this 1977 review, and you can just, again, the idea here is to get ballpark numbers, right? It's all about the ballpark numbers. And I just wanted to give you a feeler that when you and I are listening here or in our seat over Zoom and undergo quiet breathing maneuvers, the zone, this, you see, the cutoff is about 15 generations or so. The kind of Reynolds number, typical Reynolds number we'll experience are well under 10. Right? In fact, the deeper you go under mass conservation, they're going to experience creeping flows typically. 1, 10 to the -1, 10 to the -2. And when you undergo heavy breathing from running, activity, panting, then what you're doing is a kind of a translation upward of these numbers. But let it be understood that even at the entrance of the acinas, right, the first divisions that are going into the so-called respiratory zone, you know, give or take, you're still going to park at 10, right? So these are always going to be, at best, slightly inertial flows, right? But very, very quickly, because it bifurcates very quickly, then you go back into these creeping regions. So just situating the landscape. Okay, now I've kind of built on top of this, and what I wanted to bring forward here is that there's, of course, the inertial aspect and the unsteady aspect, because let us not forget that this is undergoing oscillatory cyclic breathing, right? So we bring into the picture dimensionless numbers that relate to that. One of them is called the Wormsley number. Could be a Struhal number. It depends a little bit what your background is. The point I wanted to bring is, again, whether you're in quiet breathing or in heavy breathing, if you look at this table here, then what you quickly see is that all the numbers are significantly under 1, even when you undergo heavy breathing maneuvers. In other words, that we are, to a first order approximation, witnessing what I would call a quasi-steady flow. Now, what does that mean? If you don't work so much in this area, these are transient, unsteady flows, right? We are breathing in and out. But if you think of the picture of the velocity field, the topology of the flow, it does not change with time, right? It means that if you have, for instance, a Poiseuille-like flow, it will always stay Poiseuille-like and just rescale the velocity magnitude of that Poiseuille flow. Again, I'm sure most of you know this. I just wanted to make good sense of this. So our readout, without any in-depth analysis, is telling us that this is a low Reynolds creeping world with quasi-steady flows. And I love to bring this because this is a little bit the bread and butter of where the story kicks off, is the idea of, well, if what I just said is true, then in principle, this world is completely subject to flow reversibility, right? If you go back to the Scallop theorem, so time doesn't matter. The big R is our Reynolds number here. If we're well under 1, then the pattern of motion is the same, whether slow or fast, whether forward or backward in time. Why did I bring this up? Is because for very long, there was this understanding, or at least, shall I say, a hypothesis that if that is true in the deep alveolar space, in other words, in a large portion of the small scale respiratory airways, then things should be reversible there from a flow perspective. What goes in must come out in the same way, right? And to this end, I wanted to illustrate a self-similar scale up of this curse of reversibility. I'm guessing many of you have seen a version of this video. This was back in the days when I was at the University of Pennsylvania. So you have concentric cylinders. The smaller one in the center is going to be rotating, and we're marking with 2 different colors of dye, random locations. And we're going to start rotating the barrel. And of course, you have a no slip condition at the outer wall. And the student is counting the number of cycles. 5, 6, and then 7. I think he makes it to 7. And then he goes back, right? So this is completely reversible motion, right? Because if we played this video backwards, it would be the same thing as what he's doing when he reverses. And lo and behold, this being a very viscous fluid, so that you're in a low Reynolds number regime, you have perfectly reversible motion. And I just never get enough of this video and anything to do, because, oops, the point is that us as humans, and I'm not a particularly tall one, but I still experience life from a flow perspective as being largely turbulent. In other words, we always break this reversibility and can never come back to our initial condition. But when you see it at a large scale, it's kind of impressive, shall I say. So why I say this is that a first reading would tell you that the flows in the deep space are reversible. Now, my job here, or what brought to my curiosity, is that we're going to slowly debunk this and see why it's a little bit different. As they say, it's complicated, and that's basically the gist of it. So the first thing is, we need to break down the idea that when you go into the deep space, it's not anymore a world that looks like traditional Poiseuillean tubes, right? Or vessels, right? What happens is you start to alveolate the environment. And the deeper you go through the generations, as I illustrate here with a bit of terminology, respiratory bronchial, Acinar duct, terminal sac, then you populate and populate. Now, this is a crude schematic showing this. I'm going to show you in a minute what the real world looks like. So this is what an acinus is actually. So what you're seeing here is this is amazing kind of work. You need so much diligence. So it's such a fine work. This is actually a cast, lung casts. In other words, they use liquid polymers to fill the lungs and then harden them, get rid of the tissue, and then you're left with this. And you're seeing basically a cast of the deep space. So this main figure is showing you actually one acinus, okay? Now you have to think that our body has something like, give or take, 10 to 30,000 of these guys. And in any of these guys, what your eyes are seeing is on the order of 10 to the power 4 alveoli. This is just on the right-hand side, splitting between the upper part, okay, and the lower part. So it looks very spongious, right? This is the terminal bronchiole, here, TB, RB, respiratory bronchiole, in the sense that you start seeing the first alveoli and very quickly, it's completely filled, right? So this looks nothing like grapes, right? This is much more conceptually like a sponge. And to reinforce that understanding, I'm going to show you this kind of micro bronchoscope that shows you what life on the inside looks like. Now, what you see is it looks like you're going through caves, right? This is undergoing expansion. So it's not spheres or balls that are sitting on a duct. What you need to think is that it's much more like a landscape of caves with holes, and each of these holes is the space of the alveolus. So this is an alveolus here, this is an alveolus, and you see it very nicely. So really the concept of a duct is just the negative of the space left by all the neighboring alveoli. And here in this 2D cut, you really see it's spongeous structures from conducting airways into these. And very important, unlike the concept, this erroneous analogy of using the grapes, which is, I don't understand, but it is still used in typical medical textbook. Really, every alveolus shares walls with neighbors. And that's very important from a gas exchange point of view, because you need to maximize surface area. So all of us are sharing walls with neighbors, which gives us, of course, integrity and structural strength to support the lungs and also to maximize gas. And this is shown here for you, right? That all the cuts, one neighbor sees the rest. So you understand that it's topologically a complex environment. Okay. And now one of the last pieces that go, so you've seen some topology, you've seen the anatomical landscape. This is one of the things that really kind of drove my curiosity to kick off my career in this field. So about 20 years ago already, there was this paper in PNAS, and what they did is they used, it was technically animal experiments. They do this idea of putting liquid casts, so it's a polymer that you put into the lungs, right? So these, of course, these animals will be euthanized after. And what they did is basically they recapitulate a breathing motion over several cycles by having what we call the residual volume, what's already in the lungs with one color, and bringing the tidal volume, which is what you and I are constantly breathing, in a different color, blue here, and showing how these mix. This is focused on one alveolus, okay? And then you do kind of histology. So it means that every experiment, every NUC, which is a cycle of breathing, is actually a stopped experiment and then chopping the lungs to go see. So it's not one, you can't do this. It's very, you can imagine how cumbersome these experiments are. But what you see is that the volumes, in other words, the flow, right? Because this is the under subject to dynamic similarity, is that actually it doesn't look at all reversible, okay? In fact, you see these kind of spiraling alveolar or recirculating alveolar flows. And that, for me, really was a kickoff of, wow, this stuff is really interesting, at least what's going on is the first question to be asked. And the other side of the story, to make the story complete, so you understand that something's breaking symmetry and creating these so-called reversible flows. So there's the flow, and on top of it, the superposition is the story of aerosols, which has been a big motivator in my career. And the idea was as follows. it was often, there was a premise that if particles are not diffusing, whatever that means for the time being, then actually what would go in should come out in the same way. Okay, so you have to understand that we don't have imaging modalities that really can show these transient time resolved aerosol motions nor flow motions, not at scale and not at time, and at best one or the other. So what you're seeing here is from the late 80s is the idea of a black box experiments. You have a photometer. In other words, it's just counting the particles as they pass the mouth, go into the lungs, and then counting the signal that comes back. The top represents a shallow breathing maneuver. The colors are showing you the inhalation of the bolus of aerosols of a given size, which is a micron, which is assumed as non-diffusing. That's why I kind of put it in quotation. And then the exhalation. If you breathe shallow with a shallow maneuver, in other words, I'm just going to, for the sake, show you like, and push it back, then you see that where the peak of the distribution of this particles are compared to the volume that's inhaled, so that's a shallow, basically comes back at the same peak. When you breathe very deeply, so typically when you and I are sitting in the audience here, you take something like 500. Okay, that's a normal breathing maneuver. So now if you do a deep inhalation and then you exhale it back, then what you see is the distribution of where the aerosols come out in the exhalation phase are spread. In other words, you have, lo and behold, mixed these aerosols so that they are not coming out the same way they come in. And that's the other big thing that kind of startled me. On the one hand, you have the flows in the deep airspace that are possibly irreversible. And the second piece of the superposition of aerosols is telling you that you're mixing the story. So the Scallop theorem here that I use as an analogy to kind of give us first level insight is likely not to be the right explanation. And other things are at work. So now my work really begins, so to speak. Now, when I say my work, I think it'd be much more just and fair to say that my group and others have worked to try to decipher, to understand what was going on. So the first point is, this is why I separate the story between the flows and the aerosols, right? These are two talking stories, but we need to understand them stepwise. Okay. So I told you you know, it's like there's no free lunch, basically. So if you take medical imaging modalities, MRI, CT, etc., but you want to visualize flows, then it's a tough cookie, because really, if you say you want to try and look at ventilation of the lungs, there are a few isolated techniques that are very potent, but they suffer from coarse imaging. In other words, you can't decipher what's going on at the deep alveolar level. So here, MRI of a hyperpolarized gas is amazing as a diagnostic tool. Now, it's not a standard tool. You don't just go to your physician and will you basically hook me up on a ventilation modality of my lungs. No, it's very much still a niche research like diagnostic, but nevertheless, it is very potent. And you see the kind of images of lobes, of lung lobes or whole lungs, and places. I show you under asthma, some examples, COPD, chronic obstructive pulmonary disease, or cystic fibrosis. I won't get into the details of which. I wanted you to appreciate the fact that you have snapshots in time of ventilated zones. And this is fantastic to see which zones are occluded, obstructed, constricted, lack ventilation. But it doesn't answer the question I just asked you, which is what on earth are deep alveolated airway flows? So what you're seeing is, of course, nothing like lungs, and none of the work I've done are, well, almost none of it is in actual lungs. I have some experience in ex vivo and in vivo, but I'm mostly not going to show you here. I'm going to show you what we do best in the field of fluid mechanics, is trying to understand, you know, reducing the level of complexity and step by step getting elements by raising that level. So the first thing I wanted to understand over the past decade or so is what is the nature of these cavity flows. And we've worked on basically mapping how geometry, and of course, this is only limited to a cylindrical cavity, on how low Reynolds number flows arise in such cavities done in microfluidics. So what you're seeing here is just simply you'd have these channels with changing the aspect ratio and the size. Your eyes are actually witnessing this, right? If you go from diagonal top left to diagonal top right, that bottom right, then you're seeing the change. So the extrusion out and the size of the alveolus for a fixed thickness, right? Because in this traditional microfluidics, you're just extruding the plane. The big picture is as follows, right? As you increase, basically, you extrude out, so you pull out at a given Reynolds number. So this was done here at 0.1. These are creeping flows. You pull out the geometry from left to right. Then you go from what we call I'm missing a word. This is the continuous flow. Oh, it'll come back to me, to a separated flow. So this is non-separated. That's not the word I'm looking for. And what you do is you start to witness the formation of these vortices as you extrude out. This is particle image velocimetry, or micro PIV, if you will, and some computational fluid dynamics. And what you see is as you extrude out, you start to see the formation of vortices, of these two vortices. And there's a stagnation point, and then eventually you get the formation of a single vortex, a recirculating flow. If you add, and now you stop the geometry and just look at the concept of inertia, if you go from a Reynolds of 0.1 to 1, so these are two orders of magnitude change, then you see that with inertia, you break the symmetry, you create one vortex, and it's biased on the side, on the proximal side of the flow, right? So the analogy I want to bring here, and think about it, it's not rocket science really. Think of it that way, right? This is a traditional shear flow on a cavity. Many of you, I guess, know this, and some of you are probably better expert than I am in this field. But I always show this to students, and people don't get the gist of it. But basically, take any football, any ball, and you have a duct, and the ball is basically your solid body. If you just shear it from the under, and of course you rotate that ball. And in many ways, that's kind of what you're experiencing. Why bother with all of this? One, well, as fluid dynamicists, we're interested in general flow phenomena, but I wanted to first ballpark what we're going to anticipate in the Acinar world. Now, topologically, or from an anatomical perspective, alveoli, as heterogeneous as they might be, the length scales are typically the same. So radius of half to half, right? So they're not extremely long or extremely wide. So they typically park at the 0.5 to 0.5. So you're going to anticipate that in all your regimes, you're going to be somewhere around here. And what does that mean in terms of the different flow patterns we've witnessed? That typically we only anticipate to see these single vortex configurations, which is kind of what you saw in that seminal PNAS paper, right? You had the observation of this single rotating recirculating flow pattern. Okay, now bear in mind, right? We go from simple to complex, and by complex, I mean nothing like the real lungs, but adding on elements, mechanistic elements that add to our understanding. So we've learned, that's why I put it chick, there's a world of recirculating cavity flows that potentially exists. And I say potentially because this is a huge system. Doesn't mean that they're everywhere. And that's the second, one of the second aspects I will bring is that recirculation can arise. It doesn't mean it's arising everywhere. But the other major point that we've kind of closed our eyes on is the importance of breathing. What you've just seen in these seminal experiments is that this is a static environment, right? Fixed walls. And the biggest piece that is the driver of this whole thing through breathing, which means that basically there are negative pressures that are pulling on the wall is that all these flows, please remember, all these flows, as long as you breathe spontaneously, are driven from the motion of the wall. So this is a very, very different configuration, say, than when you are unfortunately placed on a ventilator, which is a top-down ventilation, which is actually extremely harmful because we didn't evolve to be designed that way. We breathe from negative pressures that pull on wall. We don't have top-down pressure distribution from the tree. It's very important. And I'd like that to be understood because the flows ensue from the motion of the wall. So it's bottom-up system. Okay. This is probably kind of the Rolls Royce of where we got to in terms of making a microfluidic device to investigate the underlying flow phenomena. And why I say that is because this was a major step forward and took several iterations to get to a system like this. So the idea is, and again, I always say this, what you're seeing, this is not a lung. It has no pretense to be a lung, but what it's going to try to do is match the dynamic similarity, so the leading Reynolds numbers and Wormsley numbers with a system that has more or less the right length scales, the right strains on the walls, the right displacements, the right volume changes to give a sense of anticipating what the flows would be like. Just to run you quickly through, you're seeing a tree, an Acinar tree. It is not an acinus. You've just seen that the acinus is a three-dimensional space-filling network. This is a planar extruded system that has cavities along a bifurcating tree. It is symmetrical. It has 4 generations. And what is really the novelty here was that basically these are thin PDMS walls, very thin, very thin. I mean, not thin like an alveolar wall, but they were on the order of about 20 microns. And these are water chambers. So if you look back here, this is it has basically the floor plan here is the tree. Everything in blue is water filled. Above it is a water chamber. So what it is doing, in fact, it is the water exerts non-physiological pressures because these walls are harder and thicker than actual lung walls. But what we do is we match again the strains to the displacements with artificial pressures. So we base it on matching the displacement. So let me show you in practice. So what you're seeing here at 2 scales, this is half tree, and this is a close-up of the first 2 generations. These are saturated with, the suspensions are saturated with fluorescent particles. This is not for quantification. It is for our eyes to appreciate the motions that ensue from the displacement of the walls. So just to be clear again, going back to the analogy of diaphragmatic breathing, we are exerting pressures on the walls. The displacement of the walls as a moving boundary creates volume changes, and that's what's sucking in the fluid and relaxing it. So what you're seeing on the left-hand side, your eyes are already appreciating conservation of mass. Towards the proximal generations, you see faster, relatively faster flows. And as you distribute that flow in a network, the deeper ends are slow. And the other thing, which is why I have the blow up here on the right, is that you're starting to witness, at least in the proximal generations, this concept of a recirculating flow, not unlike the analogy of that ball I placed on my arm and I'm shearing it and it rotates like a solid body. And lo and behold, you're starting to visualize those. Again, I really need this to be clear in everybody's mind. The flows you're seeing are not pumped from the entrance. They are sucked in and relaxed from the wall displacements. If you invest and go through systematically the different generations of this very simple tree, it is not a real acinus, then you witness that as you have this interplay between moving walls and distributing a shear flow down a network, the importance of the different mechanisms balance and overtake one another. When you have high shear flows, then you see more something that was similar to the first paper, which is this idea of just recirculating flows with a single vortex, right? But remember that you have something like 5 to 8% strains on the wall. That's why it's not a traditional vortex. That's just a single recirculating. You see that it kind of pulls out. As you go deeper into the airway network, then what you see is that the importance of
I think we lost Josué there. Hopefully he comes back.
one, alveolar flows are complex. Okay,
Josué,
that brings.
sorry.
Yes.
We just lost you there for about 30
Oh,
seconds. But you're back now. Everything's fine. We can see the red pointer.
Thank you, Vishal. Definitely interrupt me. I'm sorry. Maybe my router from the other room is not. Please make sure to tell me if this fallout happens again.
Yeah, sure.
So I think what I'd like the audience to retain is two things. One, alveolar flows under moving walls conditions are complex. But the physiological implications of what you're seeing is that if on this simple tree, remember, we're talking 10,000 acini with 10,000, order of magnitude alveoli exist, it means that by and large, the overwhelming majority of alveoli that are in the last generation, because this is a dichotomous tree, right? So it's the power of two. Most of them are going to be living in this kind of world, where the recirculating flow is at best weak, but most likely non-existent. And that's very important to say, because in this world, the conditions for reversibility are much harder to overcome because you're just kind of inflating a balloon and relaxing a balloon. Doesn't mean you can't do it. And that's the next point I'm going to get to. All right, so recapitulating this idea, this is kind of the ad hoc mechanistic model, so to speak, of understanding this interplay. You have alveolar expansion, ductal shear flow, and as you go along the tree, the ratio of these flows, of course, the ductal expansion, how much you're moving the alveolus is more important, but by that, it means that you undergo radial flow, transition from recirculating to radial. That's the big picture, I would say. Okay, we've worked on trying to dig in, understand these mechanisms through computational fluid dynamics. And the point I want to raise is not so much, yes, it works, it doesn't work, is what does this mean from an reversibility point of view? And that's what I want your eyes to see. Now, we can't do this in the microfluidics experiments in any straightforward, easy way. But if you look at just the tracers, not the aerosols, right? This is still just monitoring the displacements of the flow. Then what you see is actually, of course, as I told you, this is basically when you're in the deep airways, when you're just, this is a 2D cut plane into this polyhedral alveolus, and you inflate and deflate, you're undergoing the Scallop theorem. So if you do this perfect reversible motion, no surprise, folks, everything comes back. But as you look here, in a world that has this recirculation, then you see that you have the birth of tracer fluid or tracer particles that are mimicking where the motion of the fluid is. Then you start over cycles, these are 8 cycles, of moving away from your point of origin because of these complex interactions of a vortex, in particular at the interfaces with the points that live on these kind of saddle regions between one flow regime to the next, between, I found the word, attached flow versus recirculating flow. Wow, that took a few slides to come back. Okay, so if you're with me till now, let's talk a little bit more about the origins of reversible flows, because even in the alveolar depths, the ones that have no benefit, so to speak, of the recirculation and just go in and out, it can't be just as easy as the Scallop theorem, obviously. All right, so I hope this doesn't make you feel too wheezy. 1 second, if you'll permit me, I'm gonna play this. This is an ex vivo, excised lung, and we're gonna top from the machine, inflate it. And I just want you to witness what happens. then. Okay, so I don't know if you're hearing also the Hebrew. This is from my lab. This is from a porcine. So it's a pig lung. Why am I bothering you with this? Not to show you that it's a literal bloodbath in the lab, because it's mostly not. What you're witnessing here is a so-called lung recruitment maneuver. Okay, so this idea of moving walls, what does it mean on a macro scale? Lungs are complex. Our whole body is complex. Everything doesn't fit a simplistic reductionist mold. Here, of course, this is not breathing diaphragmatically, but it still holds one thing that is very true either way. Either you're ventilated from a machine or you are breathing naturally. The lung tissue, as heterogeneous, as nonlinear as it is, will not open and close, in other words, recruit and relax in the same way. And that makes a lot of sense because it's a very nonlinear system. And so what you're seeing, the pinkish, the light pinkish, which is the top, what we call the parenchymal tissue, is popping up, being recruited differently depending on location. Why? Oh, I think it says my internet is unstable. Why does this matter? Because lung recruitment not being self-similar means that at any given moment, mechanistically, you have the existence of a hysteresis. The way one guy is moving relative to the other is not in phase. And second of all, excuse me, how it opens is not how it closes. To put this in more simplistic terms, while there is no physiological agreement, so to speak, in the community as to what is the right or correct way the lungs open in and out, we have anisotropy. In other words, things are not self-similar. So I just show you possible models on the right of how this expansion might be, whether first you pull the back, alveolar recruitment, so the back is being opened up before the proximal distance, or the radius of each alveoli is the first to open and then the duct. And you have different models of this. All of them, regardless which one is right or wrong or how much is what, leads to this anisotropic motion, which by definition breaks the Scallop theorem. And lo and behold, if you return to your particle image velocimetry experiments and you run this on a cycle in a given alveolus, as careful as you might try to be in trying to create perfect reversibility on the PDMS walls, these are experiments. They are flawed by intrinsically, so to speak. So it doesn't exactly move the same way when you pull on the wall and relax it. Any break of that symmetry over the cycle leads to a break in the flow patterns. And that's why actually it's not a quasi-steady flow because of the imperfections, so to speak, the reality of the way we breathe. So these well-controlled experiments are themselves holding intrinsically different wall motions throughout the cycle. And that's why the flow pattern is actually a little bit changed. And if it's a little bit changed, it means that by definition, it is irreversible. We've tried to look at a little bit playing and controlling different aspects of this irreversibility. So one is, just so people are on the same page with me, in the previous slide, what you're seeing is the way I move out is different as the way I move back in, right? So it could be like that, and then I like that. What I'm showing here is that the second ingredient to break symmetry has to do with I move out, so my flow is here in the alveolus, but the way I feed the duct is not in phase. And this, so to speak, asynchrony or phase lag between a ductal and an alveolar flow will give rise, of course, to this asynchrony, which is what you see in the top, which is perfectly in sync, versus the bottom, where you have a change, a more visual change. You need to understand all of this is sensitive to a single alveolus, but now multiply it through hundreds, thousands, tens of thousands, millions of alveoli. Of course, this takes on a whole different level. While we cannot do this in experiments, the tracer experiments, the tracer simulations give you insight on this. The color coding is just the number, a position of this flow. So it has nothing to do with anything else, but just for your eyes to see who starts where. And if you do kind of root mean square displacements on these ensembles, that you see that over these cycles, the ductal lag between the alveolus moving out and the duct pushing emphasizes this loss of reversibility over multiple cycles. Please note that this is the root mean square displacement of the ensemble compared to a length scale, a characteristic length scale being d, being a diameter. And you see that they depart the zero value. So again, if you don't remember anything, just another kind of reinforcing testimony that we're breaking symmetry. Okay, so last but not least, in a few minutes, I see that I'm running, exhausting my time. Flow, flow, flow. The guys told us that it's a reversible. If that's not enough, what else can bring irreversibility when it's time to talk about aerosols? So the same is true. Modalities to image particles in the lungs are limited either in time or in scale, resolution or temporal. And what that means is while you have interesting, useful diagnostic imaging modalities, for instance, what we call gamma scintigraphy, this is not, again, this is a research tool because it also has radiation exposure, but it helps to understand time point wise on a coarse lung level where aerosols deposit. But I think you'll agree with me, if I focus here yet now on the left, on the left image here, then you have no resolution, not just of the generation, but forget the alveolus, right? And so the idea is, in these in vitro models, can we learn something? I will say that there has been extraordinary progress in these excised lungs of animals, so not on humans, to image with light sheet microscopy. And that's what you see here. You can see both tissue and these nanoparticle deposition. I just kind of doing PR for my colleague because it's just absolutely stunning that you can quantitatively map the deposition site. So I'm not trying to tell you, what I'm trying to bridge here is not just where things deposit. The question is, what is flight like? What is the fate of an airborne particulate matter flying through the system? Okay. So let me remind everybody, if you'll allow me, that in a black box setting, lung deposition of particles is basically governed by either sedimentation in the large particle, in the super micron size, very small microns, very small nanoparticles are in a diffusive regime. And you might not know this, but there's a weird kind of bottom region that parks at about a half micron, where particles can't diffuse enough, nor sediment enough, and so you have very low deposition of these particles. Okay, so I'll give a bad example. When you think of smoking, and a lot of the smoke particles park at about 100 microns to 100 nanometers, excuse me, to 1 micron, which is by and large the smoke cloud you see go in actually comes out because you have very low deposition. This is total deposition in the black box lungs. Each curve represents basically just a line passing through individual data gathered over many, many years of different tidal volumes, right? So the deeper you breathe, tidal volume, then of course you augment the deposition. That's these, we call them these U curves. We revisited this in that Acinar model and looked at benchmark particles of given size, 100 nanometer, 500 nanometer, 1 micron, 2 micron, in a very simple model, which is just not a lung, it's not an acinus, it's just this alveolated airway tree that can breathe. So this kind of artificial guinea pig, and it's rotated upwards so that gravity points down. And what your eyes are seeing is basically, in the world of an acinus, a 2 micron particle, which to our eyes might seem tiny, is a bowling ball in the system. It is massive. And by that, sedimentation just biases where it can deposit, and it can never enter very deeply. And as you relax or go into smaller particle regimes, particle size regimes, then diffusion starts to kick off and gives you a chance to visit more spaces. But the general rule, and that needs to be usually understood actually from an inhalation therapy point of view, is that the bolus in a single breath cannot really do better than the tidal volume front. In other words, when you breathe, it's very hard to depart. And that's one of the reasons why we know, and we as a community know this, that deposited aerosols, they really mostly visit the entrances of the acinas. It's very, very hard to reach the deepest generations of the lungs. In computational fluid dynamics, just to give you a sense, you can make much more complex space filling models, which we certainly cannot do with in vitro microfluidic based models. What you're seeing here is a subacinus. So my entire computational domain is just what you see to scale. That's the best we could do on our non-supercomputers, so to speak. Okay. But with that, we learned tremendously. We did simulations of normal breathing versus deep inhalation in these complicated networks, which, by the way, statistically hold right an anatomy, branching structures to match basically what was understood. And what you learn very quickly, of course, is that you get, again, these U curves, okay? When you do a deep inhalation in terms of the deposition fraction, then, and you hold your breath, then lo and behold, of course, you can get near 100% deposition, which is, if you don't know, that's basically the reason they advocate when you do inhalation therapy to hold your breath, because you let sedimentation do its job and or diffusion to get a chance to hit the wall. But the thing that's interesting to keep in mind is that how much actually makes it into the alveolar space. In other words, how much you actually get into the cavity versus how much stays in the ductal region is quite slow when you think of a normal breath. And you really need to leverage the deep inhalation to bring that number up. So you're actually not efficient in terms of targeting. And one of the things we've worked at, because no imaging modality in the medical world can do this, is I told you, the question is, what does the life of an aerosol flying through the system might look like? And that's what these videos, I hope you can see, are showing. I don't know if with the lag it's visible. You're seeing in real time smoke particles entering into a single alveolus at a normal breathing rate. And what you see here is all the mechanistic transport properties are visible. The recirculation that takes the particle, gravity that pulls it in the negative direction, some diffusion depending on the size, because this is a heterogeneous polydisperse particle distribution. I just want to showcase that you appreciate the breadth of various trajectories that all coexist into this simple but yet quite complex dynamical system. You have the superposition of the intrinsic motion of a particle, whether it be gravity, sedimentation, and it also means that because of these interplays, the flow can pick you back up and make you depart. If you look in the two, when it arrives, it goes in, and then one of them just whoop, went back out. So everything coexists. The reason I say this is, remember, I told you it's complicated. And why is it complicated? It's very hard to determine really who's going to deposit, not just where, but if at all. Yes, I'll just finish that. We try to show this concept of this irreversible mixing in straight ducts, going back basically to the basics and trying to map out, does a tree augment this irreversible mixing or dispersion, so to speak, even when you control for limiting the amount of diffusion? And what we learn is that if you take normal diffusion, right, the ensemble just grows in a diffusive way, as we know. But in these trees, if that's what you look, I just want to show you the cloud here in an alveolated system in just a duct. So you take over cycles this population. We did this in experiments and theory, is that you get this kind of augmented dispersion effect. Now, it's not in the regime of a Taylor dispersion, because you don't get to that, excuse me, but it is there. And the reason is, as much as there is no diffusion of some particles, any slight change or streamline crossing will be irreversible to the point that you will always move away from your departing line. And then we did this in controlled liquid-based experiments. So the minute you are in a gaseous form, where the aerosol by default, even if it's at the 500 nanometer breakpoint, will nevertheless, in an Acinar scale, move away. And so this irreversible mixing, whatever you do, will always be present. You can play around with magnets and try to stir controlled deposition. I don't have time to enter this here. I wanted to show you that no diffusion doesn't always mean it's a bad thing. You can leverage it to target a bolus, but I don't have time to enter. So I prefer, my time is run short. If you're interested in these aspects and this topic, I had the opportunity to contribute a piece on this just this past year. So you're welcome to look into this. Vishal, I'm sorry, I'm crossing over the time. Thank you very much for this opportunity. And if there are any questions, I'll be happy to take them.
No worries, Josué. That was fantastic. I mean, I think I loved the way you put a story right from the motivation to aerosol deposition. It was great. Thank you.
Thank you very much.
I'll open it up for questions. Anyone in the audience, if you have any question, please unmute and go ahead and ask. Or if you want to type it in the chat, please go ahead and we'll read it out. Just while people are gathering their thoughts, I had a quick question on the cavity flow.
Yes.
How did you define the Reynolds number there? Was it based on the radius of the cavity?
No. So all experiments are controlled based on ductal flow. Any Reynolds number it's from the feeding side. It's always from the feeding. In other words, coming from the inlet of whatever your source is. We never, it's understood and agreed upon that none of the Reynolds numbers are based on the local cavity flow. They are all based on the ductal.
Okay.
So usually either, I'd like to say everybody understood, so there are no questions, right? But usually it's probably not that's the reason. But
well, it's too complex to understand in one.
No, of course, and absolutely. In any case, those who are always welcome to shoot an email or whatever. And I hope it was a good opportunity just to for you to open your eyes on this specific topic, which is intimate to fluid mechanics, whether you might not appreciate it at first.
Just another quick question on the big lung. So was air just blown into the lung, or was there kind of breathing in there, or no?
Okay. No, so it's hooked to a ventilation machine, actually much more crude than that. In this case, it's a controlled displacement of a piston with basically just moving a specific volume into the lung at a specific rate, controlling for some pressure. Okay, so it stays in a safe mode typically. And this, what you're seeing here is really more instructive. It's not in a controlled experiment as much as to appreciate the concept of recruitment of this anisotropy in macroscopic lungs, which is of course true at microscopic scales, but you can witness it on a whole lung.
Okay, yeah, makes sense. Right, there are no more questions. Please join me in thanking Josué for a fantastic talk. I think I loved it absolutely, and it was
Thank you so much, Vishal. I really appreciate the opportunity, and I hope in the future, now that your borders have reopened,
oh yes, of course,
we'll be able to visit again.
Great.
Thank you so much.